What you see running here is a program which manipulates the sine, the cosine, the tangent function, and the inverses, arcsine, arccosine, and arctangent, and also the reciprocal functions, the cosecant, cotangent, and the secant. So we've got these 9 different functions. Each function has got 3 addressing modes, so we've got 27 different functions with addressing modes that we can use within our floating point unit, or as I like to call it now, it's the floating point unit with a CORDIC unit added. So I call it this my little math coprocessor. So we can go in and have a quick look and we can see where it is. So if we head into the CPU and we head over to the floating point unit. So within the floating point unit, we've got our adder subtractor, we've got our multiplier, we've got our division unit, we've got our square root, we've got a CORDIC unit here, and a float to integer converter. So we're really interested in 2 of the things here within this video, the CORDIC unit, which is new, and also the use of the floating point divider. Now both of these units here are approximating units, okay, as opposed to the rest of them, which are the add and subtract, multiply, and the division are exact units, but the square root, the floating point division, and the CORDIC are going to be approximations. So we're interested in finding out how well the circuitry approximates. Now if we were to drop into the CORDIC unit, and you can see the CORDIC unit running away here. Now the actual CORDIC low level is here. So in this low level we've got a ROM block here which provides us with our 2 to the power of minus I values, and we've also got another block here that provides us with our arctan 2 to the minus I values. Now I worked through all of this within the CORDIC unit course, but I also worked through a cameo of it within the Design a CPU 4 course. So this is working away here at the moment. Now another thing that is interesting is that not only are we using this approximation method, which is the CORDIC unit, we're also using the approximation method for the divider and the square root. So the approximation method we used here is a fast inverse square root followed with a Newton Raphson in order to generate the 1 upon the root of our input. So these 2 nice, beautiful little bits of architecture are what are really at the heart of this math coprocessor. And in fact, I've used a couple of things in order to make the fast inverse square root algorithm a bit more accurate. So first of all, it doesn't just have 1 magic number, we've got 10 magic numbers. And also, whenever we're using the the fast inverse square root algorithm in subnormal mode, then we're going to take all of the subnormal inputs and we're going to actually generate a value within a lookup table. So that's the simulation completely ran now and it's finished, and the final outcome we've got here is in register R3, which is 50D3. Now let's have a quick look at the code. So this is the code that we've put into the machine. So this code runs the sine, the cosine, and the tangent, the cosec, sec, and cot, and also the arcsine, arccos, and arctangent. So it runs these 9 different instructions, but also runs them over 3 different addressing modes. So we've got 27 different options that we have here, and we have them all one feeding into another. So in order for the final output to be correct, the whole process of one function feeding to another, has to be correct all of the way through. Okay, so if it is correct all the way through, the final value in R3 should be 0 cross 50 D0. Now, whenever we actually go through our process within our CPU, we get 0 cross 50 D3. So we're only in effect 3 units out. So this is really very, very close. And in fact, we can have a wee look and see exactly how close this is. I've got an online tool, which I will bring up here. So this is the online tool. And from this tool, we can put in the values and see how close we are. So what we should get is 0 cross 50D0. So we should have got 38.5, but the output we get is 38.59. Okay, so we are accurate within one decimal place, and in fact we're only 0.04 out. So I'm very pleased that this is actually really quite accurate. I've also gone ahead and I have drawn in all of the functions, and the functions are able to render really well within the graphics screen. So I'm pleased with how it all works. It all looks really good and it's all holding together really well, and we can generate lots of fancy mathematical functions. Now, we haven't extended this to the full capability of the CORDIC unit as yet. We could use hyperbolic mode, and we could use linear mode, and we could use both of those modes in vectoring and rotation. But we're not doing that for the moment. For the moment, we're simply using the rotation mode. We're simply using circular mode in rotation and vectoring in order to generate all of our trig functions. And it's much better doing it this way. If I was to do it using the Taylor series approximation, it would take 10 to 20 times longer in order to do that. So it's a lot faster, a lot neater, and a much more powerful way for us to generate our functions within our CPU. Thank you for listening. I'll get you on the next video. Goodbye.